So today we're talking about acceleration, constant acceleration problems and constant velocity problems, but instead of in one dimension, we're going to be talking about them in two dimensions. And so we're going to be talking about things going down hills or up hills, and then we're also going to be talking about things moving in a circle. However, I'm going to start off the day with a little review of vector addition. And I want to explain it a little bit differently than I did last class, and I want you to think of it as like a tug of war. And so last class we kind of jumped right into vector addition in two dimensions, and I want to review what it is in one dimension. So we think of it as a tug of war, right? And you can also think of it as forces. And so if I've got a tug of war where I've got people pulling with, let's say 4 newtons of force to the left, and then I've got people pulling with 5 newtons of force to the right. Well, which way is that rope going to ultimately move? All right, so I know the stronger side is going to win, and it's going to be the side with people pulling 5 newtons worth of force. And the net result is actually going to be only 1 newton, and so it's the difference between those because they're acting in opposite directions. Likewise, I can have something pulling downward with a force of, 9.8, and we'll still say newtons for force. And then I could have somebody pulling upward on that same object also with 9.8 newtons. And what's going to happen in that case? Well, in that case, nothing is going to move. These two forces are going to cancel, and I'm not going to have any net force. And so I can begin to think of vectors as this kind of tug of war. When we move into two dimensions, this analogy actually still works. And so I can think, I like the example of someone in a rolly chair who is holding on 2 ropes. And so let's say we have our person in our chair, and one friend is going to pull the rope in this direction, and the other friend is going to pull the rope in this direction. And so these forces don't easily cancel or add or subtract or anything like that. And what I then think to myself is, okay, well, what is going to be the result of this pulling? So if I've got one person pulling up and then one person pulling right, what direction is the person in my rolly chair going to go? And I know that they're actually going to kind of go in this diagonal motion, right? And so that would be what we call the resultant of that action. Last class, you guys were asking, I could also think of this as a vector addition problem where I've got something going to the right and something going up, and I say, okay, are these tip to tail? No, they're not, so I actually need to move this arrow over, and now I can complete the triangle. And last class you guys were asking, well, how do I know if the arrow is going down and to the left or up and to the right? How do I know whether it's this arrow or that arrow? And the way that you decide is kind of thinking of this tug of war situation, right? If I've got something that is going to the right and up, then my net result is going to be a movement that is also to the right and up. Your book also has a really good example of this, and so if that example still isn't making sense to you, I really suggest you go to page 70 in your book, and these little tactics boxes are oftentimes pretty helpful. And so the way your book explains it, and this is a subtraction problem, so let's say I've got the problem of vector A, sorry about that. Let's say I have the problem of vector A minus vector B. So A minus B. In my mind, I'm going to go ahead and change that to an addition problem, so A plus the opposite of B. So I go ahead and draw vector A like they've done here. And then I have to flip vector B, and in my mind, all of that means is put the pointy end on the other end. So B is still the same size, but it's going the opposite way. And then to say, okay, well, once you've flipped B, place the tail of B at the tip of A, which is what we talked about. And then this last rule is kind of the question that somebody was getting at last class about, okay, well, where do I know or how do I know which arrow to draw? The one that's pointing up and to the right or down and to the left? And so your book says you've got to draw it from the tip of the first term to the tail of the second term. And so your arrow will always go from first term to second term, if you want to think about it like that. We also talked about acceleration vectors last class. Again, your book has a really great tactics box that explains this. But we can also think of it as vector addition. And so I know that acceleration is change in velocity over change in time. And I know that time is a scalar, so I'm not going to worry about that. And I'm going to bring down this delta V down here. It's V final minus V initial. Go ahead and change it to an addition problem. V final plus the opposite of V initial. And so I know I've got to flip my V initial vector. And then once I do that, my acceleration vector is actually going to be the resultant of those two, of that vector addition. And so we're going to continue on with this idea today. When we talk about things moving on a hill, we're going to talk about resultants, and we're going to talk about triangles, and we're going to talk about centripetal acceleration and exactly what that is. Alright, so again, a little bit of a review. We've talked about how to get the resultant of two vectors, and I've been really nice to you up to this point and given you those two vectors at a right angle to one another, and then the resultant is the hypotenuse. But you'll get to problems where they give you the hypotenuse and then they want you to find what we're calling the components of that vector. And so what is the x vector and what is the y vector? And that's what I've been giving you up to this point. If that vector is on a coordinate plane, I can very simply look and kind of follow it over and say, okay, the x vector is this many to the right, and the y vector is that many up. But on this particular one, I haven't given that to you. And so what I'm going to tell you for this particular one is that theta equals 30 degrees. And I'm going to tell you that vector A, which they've given you, is equal to 8. Right? And so then what I'm looking at is a simplified trig problem. And I've got to decide, okay, which trig function do I have to use? And so I know that sine of theta is equal to opposite over hypotenuse. I know that cosine of theta is equal to adjacent over hypotenuse. And I know that tangent of theta is equal to opposite over adjacent. And so I've got to choose, okay, what do I have here? I've got a theta, and I've got a, I've got a theta, and I've got a hypotenuse, and let's say that I'm going to ask you first for, well, what is the y component of this? In this particular triangle, the y is the opposite side, and so that leads me to the sine function. And so I plug in my values and I say, okay, I know that, I'm going to erase that cosine there, I know that I'm going to have sine of 30 degrees is equal to x, I don't really know what that opposite side is, that's what I'm trying to figure out, over the hypotenuse of 8. To solve for x, I need to multiply both sides by 8. On the right hand side, they cancel, and so in your calculator you'll need to put 8 times the sine of 30 degrees, and you'll need to make sure that you're in degree mode. Remember, we found that out the hard time last time we did trig functions. And so if you have one of those big graphing calculators that is under mode, and you'll go down to the third row and see if radian is highlighted. If it is, you need to switch over to degrees and hit enter before you can solve this problem. Once you do, you'll find that the y component is like 4 something, right? And so we can also use, we can deconstruct vectors to figure out what their components are, or simply their x's and their y's. The other thing on this side that I really want to alert you to is this word magnitude. You're going to see magnitude a lot in your problem solvings, and you're going to want to let it trip you up because you're going to skip over it. Magnitude is just a verbal form for the meaning of absolute value. And so we reviewed in class and I said, okay, well, what is the absolute value of -3? Well, it is 3. And so when we talk about the magnitude of a vector, it doesn't matter what the symbol is on it or the size, or I'm sorry, or the direction that it's pointing. What we're referring to is kind of the absolute value of that vector. And so you could pretend at some point that, let's say I give you 2 vectors and one is a 3 to the right and the other is a -10 to the left, and I say which one has a greater magnitude. Well, I'm asking which one has a greater absolute value, and it is in fact this one pointing to the left. Alright, and so this idea of deconstructing vectors also leads us to an interesting point. I know the tip to tail rule, I can do that every time, and I can use trig to figure things out, but you might get some points in time where you have some really messy problems, like both of the vectors that you're supposed to be adding are in the diagonal, right? And let's say they're like this, and I will call these vector A and vector B, and I'm going to pretend that each one of these squares is a 1 unit, and so this would be 1, 2, 3, and 4 all the way over here. And I'm just going to apply that to the whole graph. Alright, so I could do the tip to tail rule for these, right? Like I could move B all the way up to the end of A and do some trig, and I'd get this really funny thing. Or I can add the components of the vectors. And so when I look at A, right, I'll have the x component and the y component of each. A has an x component of 1, 2 to the right, and so I'm going to say, okay, I've got 2 to the right, and it has a y component of 1, 2, 3 in the upward direction, and so I've got 3. And then I've got vector B over here that has an x component of 2 to the left, right, and it actually only has a y component of 1 up. And so I can look at adding these components to one another. To the left and to the right cancel each other out to be no component in the x direction. And 3 up plus 1 up gives me 4 up. And so my resultant vector is actually 4 straight up. Right, and so I'm going to give you one more example on this particular problem. And I'm going to say, okay, let's see. I've got a vector going down this way, and I've got one going up and over this direction, and I'll call, again, let's see, we'll call that one A and this one B. When I come over here to add the components of each vector, I can say vector A, vector B, and I will put their x components here, their y components here, and go on to add them in that manner. Okay, so for A, it's got an x component of 1, 2, so I'm going to say it's got a 2 to the right, and it's got a y component of 2 in the upward direction, or in the y direction. For vector B, it also has an x component of 2 to the right, but it has a y component of -3 and in the downward direction, which is what that negative indicates. And so then I start to think of this as a tug of war, and I've got 2 to the right and then another 2 to the right, which would yield a total of 4 to the right. And if I've got in the y direction 2 pulling up and 3 pulling down, then my result is going to be 1 in the downward direction. And so my resultant is going to have an x component of 4 to the right and a component of 1 down. And so I'll come on over here, and that'll be my resultant, having 4 to the right and 1 down. Alright, we're going to begin talking about motion on a ramp, and I'm going to do that in a second video. Welcome back to part 2 of vectors in 2 dimensions. And so we've talked about how to get the components of a vector and solve for a resultant, and then how to take a resultant and solve for the components. And so what we're going to do now is we're going to begin talking about things on an incline. We'll bring in vectors in just a minute, but I want you to think about, okay, if I have, we'll use this box to represent like a skier, because I love skiing, at the top of a hill. And if I have a skier at the top of a hill who's kind of like looking down onto the slope, once they get on the slope, what's going to begin to happen to them? Well, they're going to go downhill like they're meant to do with skiing, and hopefully stay upright the whole time. And so if you then begin to think about that motion in terms of acceleration and velocity, you realize that this person isn't going to be moving at a constant velocity the whole way down. They're probably going to be moving at a constant acceleration, and so they're going to speed up all the way until the very end, until they get to a stop, and hopefully a safe stop at that. And so what we begin to look at is this person moving at a constant acceleration throughout their time down the hill. I know this acceleration is not going to be as great as if I have that same person in free fall, which is, I know if I take this hill out from under the person, they're going to fall at 9.8 meters per second squared. In this case, they're only using a fraction of that gravitational acceleration to get down the hill, and so I've got to figure out, okay, well, exactly what fraction of the gravitational acceleration are they going? And I can do this a couple ways. I can do a little bit of trig, and it's going to involve me taking an x and y axis that I have, since elementary school, had in my head like this, and I'm actually going to have to tilt it so that the x-axis is in line with the hill itself. And so in all of these problems, we're going to tilt the coordinate plane so that the x-axis lies along the hill. Now gravitational acceleration still does go straight down towards the center of the earth, and that's what's going to help us do our trig. So we pretend that we've tilted that x-axis. Now I've kind of got the y-axis going in this direction here. The y-axis still occurs at 90 degrees to the x. Okay, I'm not changing that on you, and that's okay. But I've got the gravitational acceleration now going down at some angle, and because of a little bit of geometry, the angle between the gravitational acceleration and the x-axis is actually going to be the same angle of the hill, and that's going to make things really nice for us. We can also see that when I start looking at this triangle, right, I've got this nice right angle up here, and the free fall acceleration, which I do know a value for, is now acting as my hypotenuse. And so to figure out the component of gravitational acceleration being used in my downhill motion, all I've got to know is the angle of the hill and a little bit of trig. So when I begin to look at this, I realize that I will be using the sine function, and I know that I can do 9.8 times sine theta, and that'll give me my acceleration going down the hill. And so let's say that in this particular case, that theta equals, let's make it a black diamond. It's like 45 degrees. Whew, that is a really steep hill. And so if theta equals 45 degrees, to figure out the constant acceleration that the skier is moving, all I've got to do is 9.8 times sine, and again, make sure you're in degrees, of 45 degrees, right? And then whatever that is will give me my acceleration. Now my reasonability check is that my acceleration down a hill should never ever be more than the acceleration of free fall. And the reason that is yes, things can accelerate faster than free fall. However, In this particular kind of situation, all I've got is a fraction of gravity pulling me down. Until they invent mountains that also push a person down the mountain, my acceleration on a hill or an incline is always going to be a fraction of the gravitational acceleration. So that's your reasonability check. You know, if you get 15 meters per second squared, you've done something wrong, go back and rework it. I will also tell you that this formula is going to be useful to have on your formula sheet, because while you can do the trig, I imagine in a test situation you're going to try and confuse yourself, and so this formula will always give you acceleration down a hill. You just have to know the angle. And so let's work an example. Let's say I've got this skier who is skiing down a slope that has a total length of 360 meters. For some help, I've gone ahead and told you that he's going down 170 meters. Remember, I'm tilting the x-axis to be in line with the hill, and my y-axis is coming here. Right? I can do a little bit of trig, that's fine, not a problem, but I just want to label those for you. And let's say that I want to know, okay, well, how long does it take the skier to get down that 360 meter slope? Okay, so I'm going to go ahead and draw my picture of the situation, which is great, and I'm going to write down all of my knowns. I'm going to say that the initial time is 0 seconds, and he's starting from a place that I'm going to call 0. Oops, sorry about that. My initial time is 0 seconds, and I'm going to say that he's starting from 0 meters at the top of that hill. I'm also going to say that he's starting with initial velocity of 0 meters per second. Right? Those are all of my knowns. Even though it wasn't stated clearly in the problem, you can assume those kinds of things. Right? And then I know his ultimate destination is 360 meters from where he started. Let's pretend that I want to know the final velocity of my skier. And so I look at my constant acceleration problems and I figure, okay, well, the big thing I'm missing here is, what is his acceleration down the hill? This isn't a free fall problem, and so I know I'm going to have to use this formula. But I very quickly run into another problem, which is that I don't know what the angle is. And so for me, it helps to draw out a simplified triangle, right, where I've got 360 and 170, and I say, okay, well, I know two of the sides of the triangle. Can I use a little trig to figure out the rest? And yes, absolutely you can. And so let's say I'm trying to find this angle, which is the angle of the hill, and I know I've got my opposite side. I've got my opposite side and my hypotenuse, and that sounds like a sine function to me. So I know that sine theta equals opposite over hypotenuse, which in this case is going to be 170 over 360. Alright, and I've got to solve for theta, so that means, I'm going to come down here and do that. That means that theta is equal to the inverse sine of 170 over 360. Alright, and go ahead and plug that in, and you should get like 27. 27, it might be like 27 point something. Okay, but now I've got my theta, and so now I can solve for acceleration down the hill. So my acceleration down the hill is going to be equal to 9.8 times the sine of 27, or 27.4, I think is what that ends up being. And I'll give you a second to go ahead and plug that in to find out your a of x. Alright, and once you have your a of x, your acceleration down the hill, well, now this becomes a constant acceleration problem, and I'm going to take a look at those constant acceleration formulas from chapter 2 and decide which one do I have to use of the three that I have available. The top one looks like a good option at first, but I don't have a delta t, and so I know that I'm going to have to use that v final squared is equal to v initial squared plus 2 times acceleration delta x. Whoop. There we go. And I'll let you solve that out. Do a reasonability check as well. You should get some number like 3,000, and that is too much, and if you get the 3,000 and something, you forgot to take the square root. So I know that my v initial is 0 plus this term, right, which is, I'm going to let you decide. And then my actual velocity final is going to be the square root of that term. And you should get something like 50 meters a second, but I'll let you go ahead and work it out. Alright, our last topic for the day is uniform velocity in a circle. And so I've got this picture off to the right, and I've got these terms over to the left. And this is going to be a little bit of vocabulary, and I'm going to be trying to match that up to the picture for you so that you can solve the problems about motion in a circle. Alright, so if you get on a ride at a fair, like a Ferris wheel, right, you're moving in a circle. If you have your lanyard with your keys and student ID and you spin that around, then that's moving in a circle. And you can always move in a circle at a uniform velocity, and in fact a lot of things in our lives do move in circles at uniform velocities. And so I want to take a second and define a few little things about uniform velocity in a circle. Just like we've talked about all along, v stands for velocity. Whoop. And velocity, we know the formula for that is the change in displacement over the change in time. And this only changes a little bit because for now we've got a velocity and the magnitude of the velocity vectors isn't changing, but what is changing about all of these green velocity vectors? You say, well, they're moving in different directions. It's the same magnitude, just different directions. And so the velocity is changing. And so what we're going to have to do is we're going to call delta x, or the displacement, the amount of displacement, I guess, or distance traveled from the top of the circle all the way around and back to the top for completing one revolution. What do we call this path going all the way around the outside of the circle? It's a circumference. And so I will now measure velocity as 2 pi r, or pi d if you prefer that formula. So 2 pi r is the distance around the circle over delta t. Right? Just a little modification for that. For centripetal acceleration, I know that the acceleration vectors, because of that vector addition, they're always going to point to the middle of the circle. And so we've given this kind of acceleration a special name, and it is centripetal acceleration. We calculate this a little bit differently than our normal acceleration. And so what I want you to know is that centripetal acceleration is actually equal to the square of the velocity divided by the radius. I also want you to know that it is always pointing inward. And by inward, I mean towards the middle of the circle. Ooh, there we go. X, again, is the circumference around the circle, and so we can say, you know, the displacement is 2 pi r, or pi d, both work. Totally up to you of which one you prefer. And then these two variables are ones that you have not seen before, and so I want to take a second and talk about those. This capital T stands for a word that we call the period of a revolution, P-E-R-I-O-D. And the period is kind of the time it takes. So the period is the time it takes for one revolution. And so if I'm on a Ferris wheel, it's the amount of time that it takes for me to get from the top of the Ferris wheel all the way around and back to the top of the Ferris wheel to complete one revolution. We measure period in seconds is the SI unit for time, and so our unit has to be seconds. Now the frequency is a little bit different. The frequency is kind of like revolutions per second, and so we see this is the number of revolutions in 1 second. A lot of times we express frequency as this RPM, and you might be familiar with this from like cars or records or something like that. But a lot of things that move in circles, we talk about revolutions per minute. Know that that is what this abbreviation represents, and so when you go to solve problems, if you see that a record spins at like 33.5 RPM, that means revolutions per minute. However, that's not the unit for frequency that we need. We need revolutions in 1 second, and so if you're given RPMs, you're going to have to convert it. Sometimes though you're not given RPMs and you are given a period, and so in that case the frequency is actually equal to 1 divided by the period. Alright, and so that gives you some basic circular motion terminology. A lot of the ones that you will be solving are for uniform velocity, and so just keep an eye out for that and know that if it's uniform velocity, you're going to be using the uniform velocity formulas. Alright, and so here's your homework. And I gave out a paper quiz in class. You'll find that as an attachment to this email. It is due by Monday. And because I'm giving you a quiz that's due on Monday, there is no homework quiz this weekend. Just getting that quiz done. So no more homework quiz this weekend. I do want this quiz done. I give you quizzes to prep you for the tests and so that you know what's coming up and kind of what to expect. And so you actually have a test next Wednesday in class, and it's going to be on chapters 1 through 3 in the book. I can't believe we've covered 3 chapters already, but we have. And you can expect kind of like what you're seeing on the quiz, which is multiple choice and true false. You might get some short answer. And then I didn't give you any of these on the quiz, but I told the class I have this little category that I like to call one of these things is not like the others. Or like one of these things doesn't belong. And so I gave them the example of, I'll give you kind of a grouping of words or terms. And so let's say that I give you like velocity, acceleration, time, and force. And one of these things is not like the others. I'll ask you to pick the one that doesn't belong. So out of velocity, acceleration, time, and force, well, time is the one that doesn't belong because time is a scalar, and the rest of these are vector quantities. And so I'll have 1 or 2 of those on the test for you. The class also asked about how many questions you can expect on the test. I usually do somewhere in the 20s, so I'll say 20 to 30 questions. They're not all calculation questions. Some of them will be conceptual questions, but watch out for those. Just because it's a true-false and you have a 50-50 chance doesn't mean that it's not a difficult one. You'll have to watch out for specific words. The class also asked, okay, well, we don't have a homework quiz this weekend, and you're giving us homework. Is this going to show up at any point? And so, yes, these questions, while I'm not testing them this weekend, you will have a homework quiz next weekend, and I could randomly select from these for you. I will be checking my email all weekend long, so please email me any questions that you have, and have fun rodeoing, Taylor. Look forward to seeing you next week.